Assalamu alaikum. Welcome to the next lecture. In this lecture, we'll be discussing about the three-phase system. Until now, whether we have used the DC system or AC system, we're only talking about a single-phase system. Now we will consider the three-phase system. A circuit or a system in which the AC source operate at the same source, same frequency, but at different phases are known as polyphase system. This three-phase system is a type of polyphase system. In this, all the three phases are operating at the same frequency, but they will have a different phase. So before going into the three-phase system, let us have an insight of the two-phase system. As distinct from the single-phase system, a two-phase system is produced by a generator consists of two coils placed perpendicular to each other so that the voltage generated by one lags the other by 90 degrees. In this case, we have two windings of a generator which are placed in space 90-degree apart. That means one is, let us say, at horizontal, placed as horizontal, another will be placed vertically. So the phase difference between the two will definitely be 90 degrees while generating the voltages. So this is the same case. We have a two-phase system. This is, we can say, a neutral point. In general, where two-phase system will not have a neutral point, because neutral point usually means a point where the voltage is zero. Here we cannot say that voltage is zero, but we can say it's a common point. So between this common point and this phase A, we have connected ZL1, and similarly between this point N and B, we have connected ZL2. And this is how the two-phase system, or you can say general polyphase system, works. Now, a three-phase system is produced by a generator consisting of three sources having the same amplitude and frequency but out of phase with each other by 120 degrees. In case of three-phase system, they are operating at the same frequency, having the same phase voltages or same amplitude, but they are displaced from each other by 120 degrees. So in this case, the generator has a three winding which are connected in such a way so that in space they are apart from each other by 120 degrees, and when they generate the voltage, they also generate the voltage as per this phase difference. That is, all the three-phase voltage in the three corresponding windings will differ from each other by 120 degrees. So let us first try to understand what are the different advantages of a three-phase system. The first one, the three-phase system is by far the most prevalent and the most economical polyphase system. So in this case, and it is almost indispensably used all over the world. Nearly all electrical power is generated and distributed in three phases at an operating frequency of 60 Hz in the United States and 50 Hz in some other parts of the world. In India, it is again also 50 Hz. When one phase or the two phase inputs are required, they are taken from the three-phase system rather than generating independently. We create the three-phase system. Whether we require one phase or two-phase system, we can take that from the three-phase system. We don't need to generate them independently. The instantaneous power in a three-phase system, which is one of the most important advantage of a three-phase system. The instantaneous power in a three-phase system can be constant, which is not pulsating. That means it is time independent. In a single-phase system, we saw that we have an instantaneous power. It has a constant term which was equal to VI cos of phi divided by 2, and it has also a term that was VI sine of phi, sine of 2 omega t minus phi. So in that case, this results in uniform power transmission and less vibration of three-phase machines. So power transmission will be uniform, and there will not be any vibrations in the three-phase machines. For the same amount of power, the three-phase system is more economical than a single-phase system. The amount of wire required for a three-phase system is less than that required for an equivalent single-phase system. So in that case, it is also advantageous because it requires less amount of electrical wire as compared to the single-phase system for the same amount of power transfer. One more important thing, that is actually this is related to this. The neutral current for a balanced system is zero. For a balanced system, let us say we have this three-phase system. We have voltage V at an angle of 0, Vp at an angle of 0, Vp at an angle of minus 120 degrees, and Vp at an angle of plus 120 degrees. So I will tell you how this plus 120 degree comes out. So you can see we have a neutral wire over here. So here we have a actual neutral wire here, because there will be no current flowing through this. When there is no current flowing through this, we require the wire which is placed over here very small cross-sectional area. So in that case, the wire may be the wire required may be less. In case of a single phase system, we have one we can say live wire and the neutral wire. And in case of three-phase systems, if that was similar to that, then we should have three phase live wires and three neutral wires, and the size of the three neutral wires would have been more. So here, since the current flowing through this is zero, so the requirement of the current, this neutral wire, is only single, and we sometimes omit the requirement of the neutral wire. Now, balance three-phase voltages. A three-phase voltage are often produced with a three-phase AC generator or alternator whose cross-sectional view is shown in this figure. You can see this is a winding A dash. That means one connection of the winding is connected over here, another is connected over here. Actually, it is wound like this. This is A dash. It has two ends. One end is at this point, one end is at this point. That's why this end is connected to the this end is connected. All the A, B, and C, you can see they are connected together with N, and phase A is taken outside from here, phase B dash is taken from here, and phase C dash is taken from here. They are actually two connections of the same phase. That's why it is called a CC dash. You can see at this point, the north is pointing towards C. That means this is generating the peak voltage, that is C. That means it may be at this point. And when it rotates, let us say it rotates in anti-clockwise direction. When it reaches to B dash, that means then B dash has a maximum value. And similarly, when it reaches to A dash, it has a maximum value of phase A voltages. You can see the difference in the space between A dash, B dash, and C dash. They are 120 degrees from each other. So when they are 120 degrees from each other, the voltage generated will also be 120 degrees from each other. That is like this. This is VAN. Its peak will be at this point, and VBN, its peak will be at this point, which is 120 degree from this. Or we can say the zero of VAN is at this point, and the zero of VBN will be this lagging to this VAN by 120 degrees. Same is the case with the VCN. It is lagging to this VBN by 120 degrees, or it is lagging to this VN by 240 degrees. Sometimes we can say that this voltage is leading to this voltage by 120. When you take it back like this, it will be like this, and it will be leading to this voltage by 120. That's what we have written over here. It can be minus 240 or it can be plus 120 degrees. So I hope you understood this, how the voltages are generated and how this voltage waveform changes in time, changes with respect to time. Now, a three-phase system consists of the three voltage sources like this. We can model a three-phase system like this. They may be connected in star. Star means when one of the points are connected together and taken out, that point can be taken as neutral, and other terminals of the sources are taken out, which can be called as voltage, phase A, phase B, and phase C. So, or we can have this type of system is known as three-phase four-wire system, because we have three phase and one neutral. Three-phase four-wire system. We have another system. We can connect them in delta. They are end to end are connected to each other to form a ring. Such ring type is known as a delta. and the meeting point is then taken out. This is the meeting point of one with the other. It is taken out. Here it's also taken out. Here it's also taken out. But we need to be very sure about this. The polarity should be like this. This plus has to be connected to this minus. This plus has to be connected to the minus. This plus has to be connected to the minus. We cannot connect this plus to this plus and this plus to this plus. In that case, it will be very problematic. It will result in a dead short circuit in this loop. So there are two configurations of the source in case of three-phase system. We have three-phase four-wire system, that is star connected system or Y connected system, or we may have a delta connected system. A three-phase system is equivalent to three single-phase circuits. This is equivalent to that, a three single-phase systems, and the voltage source can be either connected in Y or delta, as shown in these figures. Now, I repeat this, balanced phase voltages are equal in magnitude and are out of phase with each other by 120 degrees. You can see this is VAN. I am representing them by phasors. VAN is equal to VP at an angle of 0. Let us say I am taking this to be reference. VBN is VP at an angle of minus 120 degrees. VB is lagging to this voltage by 120 degrees. And VCN is VP at an angle of minus 240 degrees. This is minus 240 degrees. It is also 120 degrees ahead. You can see it is plus 120 degrees as well. That's why I told you that minus 240 lagging minus 240 degrees or lagging 240 degrees is also equivalent to the leading 120 degrees. This is how the three voltages will look like. And from this diagram, you can see that when we put them, their resultant, or we can say resultant of the three voltages will be equal to 0. That is actually a big advantage of the three-phase system. Now you can see it. We may do the same analysis to find whether this is equal to 0 or not. VAN plus VBN plus VCN is equal to VP at an angle of 0. This will be VP at an angle of minus 120 degrees, VP at an angle of plus 120 degrees. Changing this polar form into rectangular form and taking VP out, this will be simply equal to 1 because there will be no imaginary part. This will be equal to cos of minus 120 degrees plus J sine of minus 120 degrees. So it will be equal to minus 0.5 minus J 0.866. So this comes up to similarly cos of 120 degrees plus sine plus J sine 120. It comes out to be minus 0.5 plus J 0.86. This and this will cancel out. Minus 0.5 is minus 1 and 1 minus 1 is 0. So the sum of the balance voltage will also be equal to 0. Like the source connections, a three-phase load can either be Y connected or delta connected depending upon the applications. So we have a load can be also connected in star or Y connected, or it can also be connected in delta, and they can also be balanced. This system of load can be balanced only when Z1 is equal to Z2 is equal to Z3. This system can be balanced when ZA is equal to ZB is equal to ZC. So a balanced load is one in which the phase impedance are equal in magnitude as in phase. So they should be equal in magnitude as well as in phase. That is Z1 is equal to Z2 is equal to Z3 is equal to ZY in case of Y, while ZY is the load impedance per phase. For a balanced delta connected, ZA is equal to ZB is equal to ZC is equal to Z delta. Let us try to do one numerical and you may understand it well. Given that VBN is equal to 110 degrees at an angle of 30 degrees, find VAN and VCN. Assuming positive sequence. Positive sequence means if we go from anti-clockwise direction, we encounter A, B, and C. If we encounter A, C, and B, that's also a balanced system, but that is known as a negative sequence, negative phase sequence. So please try to remember, if we go in the clockwise direction and I encounter A, here is B, and here is C, it is known as positive phase sequence. If we go in the same direction, that is clockwise direction, and we encounter A, C, and B, in that case, it is a negative phase sequence. In both the cases, you will see that the phase voltages are balanced. They will sum up to 0. They are equal in magnitude and displaced by 120 degrees, but their phase sequence is different. In first case, we are going A, B, and C, and in second case, we are going A, C, and B. It is negative because B is at this point, A, B, C will be then in anti-clockwise direction. That is why when we go from clockwise direction, it is ACB. It means in anti-clockwise direction, it is ABC. That's why their phase sequence is negative. So here, assuming the positive sequence, that's ABC. That means here we should have A, here we should have B, here we should have C, or here we should have A, B, or C, or A, B, or C. So it doesn't it doesn't mean that A should be always at this point. We can have A here, we should have B then here, and then C, or we can have A this is B, and this is C. So in the same manner, it is given as VBN is equal to 110 at an angle of 30 degrees. This is actually the previous figure I have just shown you. So I have tilted it so that VB, you can see VB is at an angle of 30 degree with respect to this reference. This is always taken to be reference. If A is over here, that means in the previous case A was taken in parallel to this, that means A is taken to be reference. Here A is not reference is this reference line. So VBN is at an angle of 30 degree with respect to this. This is VBN. What will be VAN? VAN will be leading to this VBN by 120 degree. That means we have to add 120 degrees to get VAN, and their corresponding phase value will be C. That is, it will be 110 plus 120, that is 110 at an angle of 150 degrees. Similarly, for VCN will be 120 degree leading to this VAN by 120 degrees. So that means VCN will be equal to 150 plus 120 degrees, that is equal to 270 degrees. That is equal to 270 degrees. From here to here it is 270 degrees, or we can say from this to this it will be minus 90 degrees. That is what here. Usually we write the angles from minus 180 to plus 180. We are omitting the angles which are above. We actually convert them to so that they will fall minus 180 degrees to plus 180 degrees. This is actually plus 270 degrees. So it is when 270 can be converted into, it will be minus 90 degrees. You can also subtract 120 from this, from VBN, because VCN is lagging to this VBN by 120 degrees. When you subtract 120 from here, it comes out to be again minus 90 degrees. So balanced three-phase connections. So you can see that we have source, and this is a source impedance, internal impedance. This is the impedance of the line. This is the impedance of the load. So same cases, impedance, source impedance, line impedance, load impedance, source impedance, line impedance, and load impedance. This is a balanced three-phase system where the source are connected in Y, and here load is connected to Y as well. We can have different connections, Y, delta, delta Y, delta delta. I have shown you here only Y. In this case, this ZY per phase impedance will be equal to ZS plus ZL plus Z capital R. That is given like this. And VAN is equal to VP at an angle of 0. That is obvious. VBN is equal to VP at an angle of minus 120 degrees, and VCN is equal to VP at an angle of 120 degrees. We can also find a line voltages or line-to-line voltages, VAB, VBC, and VCA. They are related to phase voltages. For example, VAB is equal to VAN plus VNB. You can see VAB, that is the phase voltage of A. Let's say that's from here to here, phase voltage of B. When you start from here, it will be VAN. Actually, this will be VNB. This is point N, and this is point B. This point. So VAB will be equal to VAN plus VNB, or it can be written as VAN minus VBN, because we are taking it from this point to this point. We are taking it in other way around. So it will be VBN. So VAB will be equal to VP minus VP at an angle of minus 120 degrees. So taking VP outside, this will be equal to VP into 1, and this will be 0.5 plus J root 3 by 2. When you take it again in polar form, it will be root 3 VP into at an angle of 30 degrees. This can be also done by phasor form. This is VAN and this is VBN. This is minus VBN. So we can add VAN and we can add minus VBN, or minus VNB. We have to add the VAN and VNB. VNB is the minus of VBN, so it will be like this. When you add them, you get this value. So this is VAN plus VBN. It is at an angle of 30 degrees from VAN. That is why, and it is magnitude. You can calculate this also by using the parallelogram of vectors. That the summation of vectors is also applicable to the phasors. So it will again be equal to root 3 VP at an angle of 30 degrees. So in this way, you can calculate the value of VAB. VBC is equal to VBN minus VCN. It will be equal to VP root of root square root of 3 into VP at an angle of minus 90 degrees. You can see this is VB, this is minus VC, and here we will get VBC. It will be exactly equal to minus 190 degrees. You can see over here it is minus 190 degrees. Sorry, minus 90 degrees. Similarly, VCA, that is voltage VC, this voltage minus VCA, this is minus VCA. When you add them, this comes over minus. This is 120 degrees. This is 50 degrees. Sorry, 30 degrees. 120 plus 30, it should be 150 degrees as well. Or from here you can get 120 plus from here to here it is 120 degrees. From here to here it is 90 degrees. From here to here it is 120 degrees. So it will be equal to minus 210 degrees. Since I have told you the angles should be kept between minus 180 degrees to plus 180 degrees, this can be equal to root 3 VP plus 150 degrees. So thus in general, the magnitude of the line voltage is root 3 times the magnitude of the phase voltage. So in case of Y connected, the magnitude of the phase voltage should be equal to magnitude of root 3 times into the magnitude of phase voltage, where VP is equal to VAN, VBN and VCN. We know that this VP is, since we assume this VP is the RMS value of the phase voltage, and they are equal. Now calculating IA will be equal to VAN divided by ZY, where ZY is the summation of 3 impedances. So IBN will be equal to VBN by ZY. So which is equal to, I can call this as VAN, VP at an angle of 0 divided by ZY, or IA at an angle of 0, where IA is equal to VP divided by ZY. So IB is equal to VBN by ZY, where VBN is equal to VAN or VP at an angle of minus 120 degree divided by ZY. I can call this VP by ZY as IA at an angle of minus 120 degrees. Similarly, IC will be equal to IA at an angle of minus 240 degrees. We can readily see that the line currents add up to 0. You can see that line currents will also add up to 0. When they add up to 0, the current through the neutral will be equal to 0, and the voltage through neutral, which is equal to IN into ZN, will also be equal to 0. So IN, which is equal to minus IA plus IB plus IC, is also equal to 0. You can see I am not mentioned usually here. I am not shown over here. This is IA, this is IB, this is IC, and this will be IN. So in that case, this comes out to be equal to 0 in balanced system. So for general, this is the general case. Here I have not discussed the delta connected system, but from here you can do it on your own. That's very simple. For a Y connected system, phase current is same as that of the line current. I'll first mention what is the phase current and what is the line current. So phase current means the current passing through this source, and line current means current passing through this line. You can see from here the phase current and line current for a Y connected system is same because there is no other path. Same. And line voltage is square root of 3 times the phase voltage. We have just calculated this. This line voltage is square root of 3 times the phase voltage. Because this line voltage, phase voltage is the source voltage, line voltage is from here to from this line to this line. There are actually two voltages that come in this loop, and we know that how to calculate this line voltage. It comes out to be root 3 times Vp. So in case of delta connected system, phase voltages are same as that of the line voltages. Please try to remember this. I have not shown this here. It is already mentioned in the book. If you are interested, you can go through this. Phase voltages are same as that of the line voltages, but line currents are square root of 3 times the phase currents. I just show you over here. You can see it over here. Since you can see this is the phase voltage, not this one. This is the phase voltage, and this same phase voltage is connected between two lines, A and C. That means this phase voltage and line voltage is same. Here also A and B. This is VAB. This voltage is connected between line B and C. It's the same source voltage. That means the phase voltage is same as line voltage. Similarly for this line voltage, this voltage source is connected between line B and C. That means here phase voltage is the same as the line voltage. Here the phase current is like this. Phase current is line. It will be different from the line current because there will be two current. They are summing up in the line current. And that when you sum up them, like we have summed the voltage in case of Y connected, it comes out to be square root of 3 times the phase current. The line current of delta will be square root of 3 times the phase current. Now let us try to find out the line currents. In this case, we have this system. So in this case, the line impedance is 5 minus G2, source load impedance is 10 plus G8. You can see all the phases have the same line impedance and the load impedance, and the phase voltages are displaced from each other by 120 degrees. So this is the balanced system. So in this case, this ZY will be equal to 5 minus G2 plus 10 plus G8, that is equal to 15 plus G8, that comes out to be 16.155 at an angle of 21.8 degrees. Hence IA is equal to this voltage source divided by its impedance ZY, it is 110 divided by this, that is 6.81 at an angle of minus 21.8 degrees. Since the source voltage is in this figure are in positive sequence, the line currents are also in the positive sequence. So this IB can be calculated as the same magnitude, angle will be displaced by 120 degrees. That means you have to subtract 120 degrees from this. So when you subtract it, it comes out to be minus 141.8 degrees. So IC will be equal to 6.81, same magnitude, because balanced system you have to add 120 degrees to this, it comes out to 98.2. These are the three line currents. Hope you understand like this. So in this case, we are able to find out the line current, this IA, IB and IC. Now please try to do this at your home. A Y-connect balanced three-phase generator with an impedance of this per phase is connected to a Y-connect balanced load of impedance. This is the ZS. This is ZL. The line joining the generator of the load has this. This is ZL, small l. That is the line impedance per phase. Assuming a positive sequence for the source VAN is equal to this. Find line voltages. This is very simple. You can find out the line voltage VAN minus VBN and line currents. Line currents will be simply as we have just tried to do. I have given the answer. You can check and you calculate these value. You can check your answers with these answers. Now this is actually the summary of the phase and line voltages currents for the balanced three-phase system. This is for YY system. This is Y delta system. This is delta delta system. This is Y delta system. I have just told you that we have actually four types of systems: YY, Y delta, delta delta, and delta Y. And this is the relationship of the current, phase currents, this line voltages, phase currents, line currents, and phase voltage in line voltages. Now one important thing, that is the power in balanced system. So as I told you in the beginning that this instantaneous power in three-phase system remains constant irrespective of the time. Let us now consider the power in a balanced three-phase system. We begin by examining the instantaneous power absorbed by the load. This requires the analysis to be done in the time domain. Okay. For a Y-connected load, the phase voltages are like this. While the factor root 2, as earlier we haven't take this root 2 into consideration because we assume this to be a RMS value. When this is an RMS value, converting this to RMS value, this will be the maximum value, because VAN, when we write it in terms of the sinusoids, here we should have a maximum value. So it is then written like this. VP has been defined as the RMS value of the phase voltage. If ZY is equal to Zn angle of theta, the phase current lags behind their corresponding phase voltage by theta. This is also taught in the previous classes. Then that how this current lags or leads by this voltage depending upon the impedance angle. So this I is equal to root 2 IP cos of omega t minus theta. So this shows that this theta, this IA is lagging to this voltage by theta, and its magnitude IP will be equal to VP divided by this Z. Similarly, IB is equal to root 2 IP cos of omega t minus theta minus 120 degrees. So this current will be lagging to this voltage by minus theta. Similarly, IC will be this. So the instantaneous power, that will be equal to PA plus PB plus PC, that is equal to VAN into IA plus VBN into IB plus VCN into IC, that will be equal to twice VP IP. 2 is because we have root 2 multiplied to this, root 2 multiplied to this. When they multiply to each other, it will be 2. Cos of omega t is for VAN, cos of omega t minus theta is for IA. Similarly, VBN has cos of omega t minus 120 degrees, and IB is equal to cos of omega t minus theta minus 120 degrees. Applying the trigonometric identity, cos of A cos of B is equal to 1 by 2 cos of A plus B plus cos of A minus B. When we do this, that means we have to add these two, cos of A plus B, that is equal to twice cos omega t minus theta, that is this, and cos of A minus B, that is cos of this minus this, it will be equal to cos of minus theta, sorry, cos of plus theta, that is this, cos of theta. So 3 here, because you will see one cos theta will be from here, one cos theta will be from here, one cos theta will be from here. These will add up to 3 cos theta. You can see from here, when we do A plus B, when you do A plus B, this omega t, sorry, A minus B, this omega t and omega t will cancel out. This 120t and 120 will be cancel out. It will remain only cos theta. Similarly, for this case, when you do the A minus B, omega t will cancel out. 120 degree, 120 degree will be cancel out. Here will be only cos of theta. And when we add them, it will be 2 omega t minus theta minus 240, that is written over here, and this will be 2 omega t minus theta plus 240, that is written over here. Now this 2 and this 1 by 2 will be cancelled out because it is from the formula. It will be cancelled out, and we are left with only the RMS values. So this will be VP IP 3 cos of theta. Let us say this 2 omega t minus theta is equal to cos of alpha, sorry, is equal to alpha. So this term, I have written over here, this term will be equal to alpha. That means this will be equal to cos of alpha. This term will be equal to cos of alpha minus 240 degrees. This term will be equal to cos of alpha plus 240 degrees. When you open it up, it will be cos of alpha cos of 240 degrees plus sine of alpha sine 240 degrees, because for minus here we have plus here. And here we have plus, here we have minus. Cos of alpha cos of 240 degrees and sine of alpha sine of 240 degrees. You can see that okay, so this sine alpha sine 240 degree and sine alpha sine 240 degree will cancel out, and these terms they will be added. Twice cos alpha, that is this, into cos of 240, that is minus 1 by 2. So 2 into 2 will cancel, it will be minus cos of alpha. This cos of alpha and cos of alpha will be cancel out. It will be 3 VP IP cos of theta. This is very important result, because the total instantaneous power, we are calculating the instantaneous power, not the average power. In the balanced three-phase system is constant. It does not change with time as the instantaneous power in each phase. In each phase it changes, but in three phase it will not change. This is true whether the load is delta or Y connected. Chahe delta connected ho ya Y connected ho, it will always be like this. This is one of the important reasons for using the three-phase system to generate and distribute the power. So I have told you this is one of the biggest advantages of the three-phase system. Since the total instantaneous power is independent of the time, the average power per phase for either delta connected load or Y connected load will also be per phase will be equal to P by 3, and average will be same as that of an instantaneous value because it does not change with time. So per phase value will be equal to Vp Ip cos of theta. Total three phase power will be equal to 3 Vp Ip cos of theta. Similarly, reactive power per phase will be equal to Vp Ip sin of theta. The apparent power will be equal to Sp, that is Vp into Ip. The complex power per phase will be Sp, that is Pp plus JQP, that is equal to Vp into Ip star. Where Vp and Ip are the phase voltage and phase current with magnitudes Vp and Ip respectively. The total average power is the sum of the average power in the phase, that is Pa plus PB plus PC, that is 3 PP, that is 3 PP IP cos of theta. So in terms of line values, then we write it this 3 in terms of root 3 into root 3. So it will be equal to root 3 into root 3 VP IP cos of theta. So root 3 into VP for Y connected load will be equal to VL, and for VL, IP and IL, that is phase current and line current, will be same. So total for a Y connected load will be equal to root 3 VL IL cos of theta. So in case of delta connected load, is again I will write it as root 3 into root 3 VP into IP. So VP in case of delta connected load is equal to VL. I will simply replace this VP by VL, and 1 root 3 into IP will be equal to IL in case of delta connected load. It again comes out to be equal to root 3 VL IL cos of phi. So this relation is hold good for delta as well as for star. So for Y connect load, IL is equal to IP, but VL is equal to root 3 VP, whereas for delta connect, IL is equal to root 3 IP, VL is equal to VP. Thus equation this applies to both Y connected loads as well as delta connected load. Similarly, total reactive power will be equal to 3 times VP IP cos of theta, which is equal to 3 QP, which is equal to root 3 times VL IL sin of theta. These two are very important relations you need to remember. So complex power will be equal to 3 times VP IP star, or 3 times IP square into ZP, or 3 into VP square by ZP star, where ZP is equal to ZP angle of theta is load impedance per phase. ZP could be ZY or Z delta depending upon whether the load is connected in Y or delta. Alternatively, this S complex power can be written as root 3 VLIL at an angle of theta, that will be the power factor angle, or P plus JQ. Remember that VP, IP, VLIL are the RMS value, and theta is the angle of the load impedance for the angle between phase voltage and the phase current, or we can see it is a power factor angle. Now let us try to understand this by doing one numerical on the same circuit which we have just described. In this case, we need to find out the value of average power, reactive power, complex power at the source end and at the load end. So we have already calculated the value of IA from the previous numerical. So we'll calculate this. SS will be equal to 3 times minus 3 times VP IP star. This is actually absorbed. That's why here it is 3. Usually the source delivers the power. That means we need not to have this minus over here. I will just tell you why it has taken this minus over here. So it comes out 3 times VP, that is 110 angle of 0, multiplied by this current. It is star. Star will be, its magnitude will remain the same, and its angle will change its sign. So it will be equal to 2247 at an angle of 21.8. This comes out minus 2087 plus G834.6 VA. The unit of complex power is VA or MVA or kVA. The real or reactive power absorbed, average power absorbed is minus 2087. Actually the source will supply this. In that case it will be plus 208, and the reactive power absorbed is minus 834.6. so at the load end, SL is equal to 3 times IP square into ZP. So ZP is this, that is the load side, not the line side. So this comes out to be this, IP is this. You can multiply this, you will get this value. So this is the amount of real power absorbed by the load, and this is the amount of reactive power absorbed by the load. The real power absorbed is this, and the reactive power is this. The difference between the two complex power is the complex power absorbed by the line, that is 5 minus G2. To show that, you can calculate the complex power that is absorbed by the line as well, that is 3 times IP square into ZL, that is this. It comes out with 695 point this minus this, and you will see the difference between these two, source and load, will be equal to this much. So that this SS plus SL plus SL is equal to 0. Actually it should have been SS is equal to SL plus SL, since it shows all the quantities or all the source, line and load are absorbing. In that case the equation becomes like this, and that's why we have taken here minus absorb. Otherwise it should have been SS should be equal to SL plus SL. So it will definitely be equal to 0. Now one more numerical, this is very important. A three-phase motor can be regarded as a balanced while load. The three-phase motor draws 5.6 kilowatt, that's power, and the line voltage is 220 volt and the line current is 18.2 ampere. Determine the power factor of the motor. We know that S is equal to root 3 VLIL, that is this much. So we have calculated the apparent power. Real power is given. Real power is given 5.6 kilowatts, that is 5600 watts. And this real power is, as we know, it is equal to S cos of theta. So we can guess this cos theta P divided by S. So P is 5600, S is equal to this. This is the power factor of the motor. So this is the homework. Calculate the line current required for a 30 kilowatt three-phase motor having a power factor with a lagging. If it is connected to a balance source with the line voltage of this. This is again the same problem. The only thing is that in the previous problem you have to calculate the line voltage. Sorry, power factor. In this case, power factor is given. You have to calculate the line current. Okay, thank you.